Welcome back. In this lecture, we continue with the discussion of Huntley's extension. That is, we would be using the extension of dimensional groups to reduce the number of non-dimensional pi numbers. Let's consider a simple example of a torsion of a shaft. A shaft is subjected to a torque T at this end. It is attached to a wall at this end. The twist phi of the shaft is a function of T, G, R and L. We use the dimension M, L and T. The T, time. We use the basic set of T, G and R, and then we obtain a functional relationship that phi is a function of T divided by G R cubed and L by R. Then, as in the last lecture, we could use the information that twist should be directly proportional to the length of the shaft. More the length, more would be the twist, linearly proportional. So, the relationship between phi and L should be linear, and that's why the relationship should be phi should be L by R into a function of T divided by G R cubed. We know from our theory of mechanics of material that this function of T divided by G by R cubed is simply T by G R cubed, and so that the twist is L into T divided by G R raised to the power 4 times a constant. But can we improve the result from dimensional analysis alone? And we do it breaking them into the component length dimensions. Let's take dimensions in x, y and z coordinates. Writing the dimension is not easy, so please pay attention. The force that is twisting the shaft, in fact, is a torque that is twisting the shaft. The torque arises because of force that we apply, and the force would have a dimension mlx t raised to power minus 2 or mly t raised to minus 2. In fact, the whole problem is symmetric in x and y. Z is a special dimension, but not x and y. X and y interchangeable. So, to preserve axial symmetry, we can take the dimension of force as m lx raised to power half, ly raised to power 1/2 and t raised to power minus 2. So, instead of lx or ly, we write lx raised to power half, ly raised to power half. This preserves the axial symmetry, symmetry between lx and ly. Z is along the axis of the shaft. Similarly, the radius of the shaft, which is anywhere in x and y plane, and to preserve the axial symmetry, we write the dimension of R is lx raised to power 1/2, ly raised to power 1/2, and then the dimension of the torque would be force times the radius, and we can write it as m lx ly t raised to minus 2. And then the dimension of G, the shear modulus, shear force per unit area divided by the angular strain. Force, as we see, is m Lx raised to the power 1 half Ly raised to the power 1 half T raised to minus 2. The area is Lx Ly. And the angular strain we write as R divided by length in the z direction. So the angular strain is written as this. If we were not using direction, this would simply be dimensionless. But it's actually in the R direction divided by in the z direction. So it is written as Lx raised to the power 1 half Ly raised to the power 1 half divided by Lz. So this gives the dimension of G, the shear modulus, as m Lx raised to the minus 1 Ly raised to the power minus 1 Lz T raised to minus 2. Notice that as in everything else earlier, Lx and Ly carry the same dimensions, denoting that the problem has symmetry between x and y directions. So this is the table of dimensions that we construct in M, Lx, Ly, Lz and T system. The dimension that we have calculated on the left has been transferred to this table. We use these 4 quantities as the basic set, and so we get only one pi number. Phi has a dimension of torque raised to power 1, G raised to power minus 1, R raised to power minus 4, L raised to power 1, and so we get phi G R raised to power 4 divided by T L as constant. Or the twist phi is function C T L by G R 4. A very powerful result. Single constant can be obtained by twisting a single shaft and measuring its twist. We can obtain the value of C, and this will give you a relationship between twist and torque for any circular shaft of radius R, length L and shear modulus G. Let's consider next an example from fluid mechanics. Let us consider a terminal velocity of a falling sphere in a viscous fluid. As a sphere falls in a column of viscous liquid, it accelerates initially under the combined influence of the weight and the buoyancy force. As it accelerates, the drag develops in the opposite direction, which increases with velocity. And when the velocity reaches such a value that the drag balances the net wet weight of the sphere, that is the weight of the sphere minus the buoyancy, then the sphere is said to have acquired a terminal velocity, a constant velocity which does not change. The terminal velocity has a great value in problems involving, say, a parachute. So this terminal velocity would be a function of the density of the solid sphere, the diameter d of the sphere, the density of the liquid rho f in which it is falling, the viscosity mu of the liquid, and of course the acceleration due to gravity. in terms of x and z and y coordinates, the velocity v has a dimension of z t raised to minus 1. The density rho s of the solid has the dimensions of mass per unit volume, and the volume is like x, y, z. So these are the dimensions of the solid. Same are the dimensions of the density of the fluid. The diameter of the sphere has xy symmetry. So we write this as x raised to power minus 1 half, x raised to power 1 half, and y raised to power 1 half. G is in the z direction, so it is z raised to power t minus 2. We have to worry about dimension of viscosity. How do we obtain the dimension of viscosity? We obtain with the relationship of the viscous forces from Newton's law of viscosity. The viscous force F is mu times area times the velocity gradient dv by dz. And so the dimension of mu would be the dimension of force in the z direction, mz t raised to minus 2, divided by the area, which would be yz, the side area of these, and the velocity gradient in that direction of the velocity field. So that would be z t raised to power minus 1 as velocity and d velocity by dx. So these are the dimensions that are obtained as m z minus 1 t. These are the two formulations, and from this we get this result. Out of these we can form two pi numbers. One pi number would be rho f by rho s, which is obvious since the dimension of f and s are same, and the other pi number is v mu divided by rho s g d cube. So that this pi number, which contains the dependent parameter terminal velocity v, should be a function of this parameter, which is written here. So v is constant times rho s g d square by mu times the function of rho f by rho s. As we had argued in a previous lecture, that in this problem of terminal velocity, the only thing that matters is the weight of the sphere. So it is not rho s or rho f independently in this, but it should be the difference rho f minus rho s. So this parameter should have a form of rho s minus rho f divided by rho s, or 1 minus rho f divided by rho s. So that the terminal velocity v can be written as constant times g. Only one pi number involved. And we can do the experiments and can easily find that this constant is 8 by 9. So this is the relationship for the terminal velocity of a falling sphere in a viscous liquid. Notice again that it is the use of dimensions that decreased the number of pi numbers formed to the ideal number 1. So we ended up only with 1 pi numbers. Of course, we have used the fact that the density of the fluid should enter only in the combination 1 minus rho f by rho s. Another example, capillary rise of a fluid. We know that the surface tension causes the fluid to rise in a capillary. For fluids that wet a surface, for fluids which do not wet a surface, like mercury in glass, there is a depression, but that is the same phenomena. The H, the capillary rise or capillary depression, is a function of sigma, the surface tension, d, the diameter of the capillary, rho, the density of the liquid, g, acceleration due to gravity, and theta, the wetting angle, the angle that the surface makes with the horizontal. Theta is 0 for a liquid like water on glass and is 180 degrees for mercury and glass. Actually, if we work in a direction coordinate, then this force, for example, if this is the meniscus, the force is at this angle. The component of surface tension force which is responsible for the capillary rise is the vertical component. This is the angle of contact. The horizontal component has nothing to do with the capillary rise. So, it is not sigma and theta independently, but sigma cos theta that should enter our formulation. So, capillary rise H should be a function of sigma cosine theta, d, rho and g. We work in Lx, Ly, Lz and Mt system, and we write the various dimensions. These are easy to write. We use the basic set that consists of these parameters, and then there is only one other variable left, the dependent variable h, the distance through which the fluid rises, and in terms of basic set is a dimension of sigma cosine theta raised to power 1, rho raised to power minus 1, d raised to power minus 1 and g raised to power minus 1 again. So, this pi number is a constant, or h is c sigma cosine theta divided by rho d g. This is a formula that you would have obtained in your fluid mechanics course. For water, cosine theta is 1 because theta is 0. The wetting angle, the contact angle is 0 for water. Let's do this last example of free convection on a vertical plate. We have done this example earlier and obtained some results. The heat transfer coefficient H is a function of the fluid property rho, mu, k and Cp. The Z, the length of the plate in the vertical direction, the temperatures TW and TF, the wall temperature and the fluid temperature far away from the plate. Beta, the coefficient of expansion of the fluid with temperature, and G, the acceleration due to gravity. We had argued earlier that in a heat transfer problem, it is not the temperatures that matter, but the temperature difference that matters. So TW and TF were replaced by delta T, the temperature difference, TW minus TF. And we also argued that the expansion of the fluid contributes to free convection through the action of gravity. And so it is not beta and G independently that should enter the formulation, but together. So this should be G beta. We had reduced the number of parameters by 2 previously. This is how we did it. And when we solved this problem last, we obtained Hz over K, which is Nusselt number, is a function of Grashof number and Prandtl number. This is the functional relationship that we obtained 2 classes earlier. Can we improve this result by directional analysis? It is possible to improve this result when the length dimension L is broken up into 3 mutually perpendicular dimensions Lx, Ly, and Lz. So the problem with the reduced number of parameters, that is on using delta T and G beta together. Now the dimensions of H in terms of directions are obtained from the relationship Q is equal to H delta T. Q is the heat flux, the heat transfer per unit area. H is the heat transfer coefficient. Q dot is heat flux Q times the area, and the area would be like this on the plate. It will have the dimension Ly, Lz, not x. So that the dimension of H would be given by this. Dimension of mu are obtained from the Newton's law of viscosity, tau is equal to minus mu dV by dx. This is the wall. The viscosity, viscous force would be in that direction. So dimensions in terms of direction would be m Lz t minus 2, and which would be tau, the stress, times the area, which is Ly Lz. So dimension of tau, the stress, would be m Lz t minus 2 divided by Ly Lz. The dimension of velocity gradient dV by dx, the velocity is Lz t minus 1, and dx in the x direction Lx. So divided by dx would convert to Lx raised to minus 1. And using these two in this equation, we get the dimension of viscosity as these. The dimensions of K, the conductivity, are obtained from this relation. The heat flux is minus K dt by dx. Dimensions of Q have already been obtained as this. And so dimension of K are obtained as these. You can verify them. So, with a bit of patience, we can construct a matrix of dimension of all our parameters here and the dimensions here. These are the thermal quantities Q and theta, thermal energy and temperature. The length is broken up into these three, and mass and time. A total of 7 dimensions. we write the dimensions here. All of these have been obtained in the last few slides. We use the 6 quantities as the basic set, and then we have only 2 other quantities left, one dependent and one independent. And we can formulate their dimensions in terms of the basic set as in this table, and then can write the functional relationship. The dependent pi number is a function of independent pi number. This is simplified to give hz by k, which is Nusselt number, and this is equal to Grashof number raised to power 1/4 into a function of Prandtl number. So that this is the relation. The last time we did it, we obtained Nusselt number as a function of Grashof number and Prandtl number. How it depends upon Grashof number was not obtained by dimensional analysis, but using the directional analysis as presented here, we have been able to establish that Grashof number should enter the relationship as 1/4 power. So the Nusselt number is like Grashof number raised to power 1/4 times a function of Prandtl number. This will also require a number of experiments to establish the functionality of Prandtl number. But the number of experiments required now would be far fewer. This illustrates the power of directional analysis. Thank you.